At the end of the guide, we have a few topics that are little bits and pieces of content that aren't really related to each other, but just some things that we need to review for further use later on. So the first thing that we're looking at is what is a polynomial, and how do we determine whether an expression is a polynomial or not. So remember that polynomials are a group of terms being combined or made up of coefficients, so that would be the number part, and perhaps a variable, that would be the letter parts. If there is no variable, then we call that a constant. But for the most part, the terms of a polynomial are groups of terms that are coefficients and variables. And so when we are looking at the degree of a polynomial, we're looking for the highest power. So a degree is the highest power in that group of terms. And the leading coefficient is the coefficient on the highest power. So remember, with polynomials, when we are defining a polynomial, we want any exponent to be a whole positive number. So we don't want to see any negative exponents, and we don't want to see any fractions or decimals as exponents. Okay, so we want whole numbers. So the natural number set, think of natural numbers starting with 1. Starting with 1 and whole numbers. Kind of think of it as perhaps standing in line, and we are describing your position in a line. So I'm either 3rd in line or 10th in line. We could not be 0.8 in line. We could not be 3/4 of a spot in line. So it has to be a whole natural number. So when we are defining a polynomial, we're looking for all terms to have whole positive exponents, and we're looking for the degree. So this one fits the definition of a polynomial because I see all my exponents are whole positive numbers. The degree is 3, that is the highest exponent, and the leading coefficient would be the coefficient on that degree or that highest exponent, which would be 2. The second one also fits the definition of a polynomial. I see all exponents are positive numbers, so it is a polynomial. The highest degree is 4. So keep in mind that they won't always be in order. Sometimes the degree or the highest power is not at the beginning. So in this case, it's -7x4. So the leading coefficient is -7. Let's skip down to number 4. This one is not a polynomial. And the reason being is this term. If I write this term as an exponent, I'm going to move that x to the numerator, and since I'm moving it, it's going to become a -1. And so that term here means that we have a negative exponent, so that means that it is not a polynomial. So that's just a quick definition of what a polynomial is, whether to identify if it is or not, determine the degree, and leading coefficients. The second thing in that end of the guide is just finding the zeros. So remember that zeros are finding the value of x when y is 0. So in other words, you're finding the x-intercepts of the function, which we sometimes call zeros because it is finding the value of x when y is 0. So that makes sense that we call them zeros. Sometimes we call it roots. Sometimes we call it the solution, because when we are asked to solve, we are saying what is the value of x when y is 0. So those are just different names for the zeros. So in order to find the zeros, you need to have it in factored form. So 3 and 4 are already factored, so that makes our life a lot easier. All we do is take each factor, set it equal to 0, and solve for x. So we have 1 at 4, set it equal to 0, solve for x. We have 1 at -5, set it equal to 0, solve for x. And we have 1 at 5/2. So if it is in factored form, it is pretty easy to find the zeros or the roots. Don't worry about any leading coefficients. There is no variable, so we don't use that to find a 0. If the equation is not factored, we need to factor it first. So for example, in question 1, it's a simple trinomial. I want two numbers that multiply to get 30 and add to get -11, so that would be -5 and 6. And then we solve each factor to determine the 0. There may be some harder trinomials to factor, but we've already reviewed this. Let's see, 4 3s are 12. So 3 3s are 9, -4 is 5, so let's make this -9 plus 5, and then we'll just solve for x. So factor however method you prefer. I just did that one in my head, but if you want to do decomposition, that's fine too. So if you want to find a 0, it needs to be in factored form. Now in this question we have the reverse. So instead of given an equation and asked to find the zeros, we're given the zeros and asked to find the equation. So the zeros given are 2, -3, and 4. And so we want to set these equal to 0, so we're going to move the 2 to the left so that equals 0, and then that will become a factor. So we're just reversing what we did in the previous question. We'll move the 3, and that becomes a factor, and then we'll move the 2 to the left, and that becomes the third factor. So the factors are x minus 2, x plus 3, x minus 4. It wants it in factored form, so I don't have to expand it. What I don't know, so this is what I've found so far. I've got a factor at 2, I've got 1 at -3, and I've got 1 at 4. So if that was the only information given, I don't really know what it looks like. I know it passes through those 3 points, but it could look like a lot of things. Let's do one. So if I could have a graph that passes through these points that looks like this. I could have a graph through these points that's maybe a little steeper. I could have a graph that maybe goes the other way. So these are lots of different possibilities that have these same roots. So we call that a family of lines. So a family of lines might have one property in common, and that's being the roots. Other than that, I don't really know what it looks like. So in order to narrow it down to one specific line, I need to determine what that stretch is. Is it tall? Is it skinny? Is it reflected? And so in order to do that, I need another point. And they do give us a point that's on the line. So we're going to substitute that point into the equation so that we can determine the stretch. So let's just do it in red. So I'm going to put 48 here, and then I'm going to find the value of A when x is 0. So I'm going to put a 0 in for all these x's, and y is 48. So we're going to solve for A. So this bracket is -2, this is 3, and this is -4. So that gives me a value of 24. And so A would be 2. So once I know the stretch, I can narrow it down to one specific line rather than a family of lines. Now I have one specific line with a stretch of 2. The only thing to watch out for is roots that are maybe given as a fraction. We don't really want to put fractions in our factors. So one factor would be x plus 1. 1 factor would be x minus 4. Now this 1/2, I don't really want to put a fraction in a factor because it's not really proper form. We like to have just whole numbers. So what we can do is multiply the 2, cross multiply to make that 2x, and then move the 1 to get our factor. So this way we're not using fractions in our factors. And then once we've done that, we will need a point to substitute in to find the value of a. So at this point, I would then substitute in the point to -3, and that will allow me to find a. Then there's a little bit on finite differences. So if you remember from grade 9, grade 9 was entirely about whether a function was linear or nonlinear. And how did we determine that? If we had a table of values, we looked at those first differences. So we looked at the differences in the y values. So we can find that by just subtracting a y value from the y value before it. So I would do -8 minus -27 to find that difference, and then I would do -1 minus -8, and so on. So if that first difference was the same, I would know that the line was linear. If it's not the same, I would know that it's not linear. Then I could do it again. So the second difference is determined. If the second difference is the same, it would be quadratic. So if the first difference is the same, it's linear, so the equation would be y equals x. If the second difference was the same, the equation would be quadratic, and y equals x squared. If I have to do it a third time, this is a cubic function, so I know it's going to be y equals x to the power 3. So the number of times I have to find the differences, that will tell me the degree of the function. So if I have to do it once, it's a power 1. If I have to do it twice, it's power 2, and so on. So that's all you're doing with these. We're just looking at those first differences. So we do -3 minus 1 is -4. 5 minus -3, so that's like adding, so that's 8. 37 minus 5 is 32. 105, might need my calculator for this one. 105 minus 37, oops, is 68. And then 221 minus 105 is 116. So since the first differences are not the same, we know that it's not linear, so we're going to do it again. So we're going to do 8 minus -4 is 12. We're going to do 32 minus 8, which is 24. We'll do 68 minus 32, which is 36. And we'll do 116 minus 68, which is 48. Again, second differences are not the same, so I know it's not power 2, so I'm going to do it again. 24 minus 12, 36 minus 24, and 48. So once I get that constant value, that tells me the degree. That tells me it is a cubic function. If I wanted to know if the leading coefficient was positive or negative, well, that's going to be determined in whether that constant value is positive or negative. So since 12 is positive, it's going to have a positive leading coefficient. The next item is transformations. So you've been doing this since grade 10. In grade 10, we looked at transformations of quadratics. In grade 11, we looked at transformations of all functions. Well, mainly linear. What else did we do? We did quadratic. We did 1 over x, rational expressions. We did square root functions. So we looked at different types of functions, but the transformations always stay the same. So a couple of things to keep in mind with transformations. First rule is if the transformation is outside the function, so the function being f of x, this is my parent function or my starting function. So if the value is outside that function, either before or at the end, it's always going to be a vertical transformation because it is being applied after the function. So let's say, for example, the function is x squared. I'm going to square first, and then I'm going to apply the function. So that's going to change the y coordinate, which is a vertical value. If it is inside the bracket, so C and D, it's going to be a horizontal transformation. So that's the first thing. Is it inside the function or outside? Inside the bracket or outside? Outside is vertical, inside is horizontal. The second thing to look at is the operation. Is it multiplied, or is it added or subtracted? So the three types of functions we have are translations, which is another word for shifting. We have dilatations, which is another word for either stretching or compressing. So think of your eyes dilating. They either get bigger or smaller, or your pupils. And then we have reflections. So if it is multiplied, it is going to be a dilatation or a stretch or compression. If it is bigger than 1, it's considered a stretch. If it's a fraction or a decimal, it's considered a compression. So A is multiplied, so it's going to be a vertical stretch or compression. And B is added, so it's going to be a shift. It's going to actually move the graph. Likewise with horizontal, C is multiplied, so that represents a stretch or compression depending on the number. And D is subtracted, so it is a shift. So two things we want to look at. Is it vertical or horizontal? Is it a stretch or a shift? And then reflection, of course, are those negative values. And then the last thing to keep in mind is that horizontal transformations always do the opposite. Vertical transformations will do exactly what they say they're going to do, but horizontal transformations will do the opposite. So if you think of mapping notation, the inside values are going to affect the x coordinate or the horizontal. So C and D are going to do the opposite. So if it's C, it'll be 1 over C times x, and if it's minus D, it will be plus D. The y or vertical transformations always do exactly what they say. So A and B multiplied by A added B. So the function that is given as the example, so the parent function in this case is x to the power of 3. That's what we're starting with. And we'll kind of go from left to right. So 6 is a vertical stretch. It's outside the bracket. It's multiplied, so it's a stretch, and it's bigger than 1. And we say by how much? So you always say vertical, horizontal, what type of transformation, and by how much. Keep in mind that the negative is not, you can't stretch a function by a negative value. Okay, a stretch or compression always has to be a positive value because you're measuring the distance that it has been stretched or compressed. So the negative is a reflection, and since it's outside the bracket, it is a vertical reflection. And we might say in which axis it is being reflected. So think of a vertical reflection. If I have this graph here and I'm reflecting it vertically, positive y's are going to become negative y's, and so the mirror line is the x-axis. So we might say it is a vertical reflection in which axis. If it's vertical, it's going to be reflected in the x-axis. If it's horizontal, it would go the other way and would be reflected in the y-axis. The 4 is inside the bracket, so it's horizontal. It's added, so it's a shift. And remember, x does the opposite, so it's going to go left 4 units. So it's not going to go right, it's going to do the opposite, so it's going to go left in the negative direction. And then finally, the 7 is outside the bracket, so it's vertical. It's subtracted, so it's a shift, and it's negative, so it's down, and we say by how much. In this part, the last part is determining whether we have even or odd functions. So this is not even or odd degree, it is a even or odd function. So the definition of an even function is that if we replace all x's with negative x, we get the same graph. So what does that mean? Well, graphically or visually, here's my function. Let's say this is f of x. If I change all those x's to negative x's, but the y's stay the same, right? So I'm changing those x's to negative x's. If the y's stay the same, what is happening is it's going to be a horizontal reflection in the y-axis. So if your graph reflects horizontally in the y-axis, if you change positive x's to negative x's and you get the same result, then it is considered an even function. And sometimes we say it has line symmetry because it reflects in a line, the line being the y-axis. So sometimes we say that has line symmetry. An odd function is we're going to do the same thing. We're going to change those x's to negative x's, but with an odd function we get the opposite results. So when x is replaced by negative x, we get the opposite result. So what does that mean? That means that if x changes to negative x, so let's say this is our original function. So we change x to negative x, and then the y also changes. So basically the x goes to negative x, the y changes to the opposite. We get an odd function. So we can say x becomes negative, y becomes negative. I don't know why this is doing this. And so we can also say that it's rotating around the origin 180 degrees. And the reason it's 180 degrees is because it's flipping left and then down. So those points are 180 degrees from the original points. So sometimes we say it has point symmetry because we are rotating around the origin, which is a point. So if you replace x with negative x and you get the opposite result, we say that is an odd function. So how does that work? Well, let's look at these ones which are graphs. So in the first one, I'm going to say this has point symmetry because here's my original. And I can see that this has been rotated around 180 degrees. The positive x became negative x, and then the positive y became negative y. So we would say this has this is an odd function or has point symmetry. This one, here's the original. It looks like it's been reflected in the y-axis. So I would say that is an even function or has line symmetry. This one is neither because it is not reflected in the x or the y-axis and it doesn't rotate around the origin. This one, here's the original. Let's do this in blue. Here's the original. So this one looks like it's been flipped left and down to get this result. So I would say again this is odd because it's 180 degrees from its original position. If it is an equation, so how do we do it algebraically? So you can't just say it's odd or even or neither. You need some proof, right? We always require proof. So what's my proof? My proof is to replace x with negative x. That's my proof. You don't want to just replace it with a number, because if you replace it with a number, let's say -1, you're only testing for that one number. So you want to test for all values. So what we do is we replace x with negative x. So x becomes negative, and then we're going to square it. Well, negative x times negative x is positive x squared. And since the equation stayed exactly the same, then we would say this is an even function. If f of x equals x to the power 5, again, we're going to replace x with negative x. And we're going to apply the power 5 to that. So that's negative 5 times its, or negative x times itself 5 times, which means we're going to have an odd number of negatives. So it would be negative x to the power 5. Since it is exactly opposite sign to the original, we say that is an odd function. This one we have x squared, so x becomes negative x plus x cubed. So negative x squared would become positive x squared. Negative x to the power 3. Well, now I have 3 negatives, so that means the result will also be negative. So x squared stayed the same. It's still positive. X cubed is now negative. So the first term changed, but the second term didn't. Or sorry, vice versa. The first term stayed the same. The second one changed signs. So it can't be a little bit of one and a little bit of the other. It's neither. It can't be partly even and partly odd. So we say it's neither. It's not completely the same, and it's not completely opposite.